Now that we know how to construct graphs, let's look at how they can be misleading. Questions to ask yourself when looking at data or graphs. Is the information presented correctly? Is the graph trying to influence you? Does the scale use a regular interval? What impression is the graph giving you? Statistics can be misleading. The main purpose of this class is to learn enough about statistics to know when the facts are being misrepresented or when a study has been done so poorly that conclusions should not be drawn. Statistics are often provided to support a position and can easily be twisted in favor of that position. The purpose of this lesson is to learn how to recognize techniques commonly used to deceive. One such technique is bad sampling. When a sample is used to represent a large group, it must be representative of the entire group. This was discussed in a previous lesson. If the sample is bad, the statistics are meaningless, so there is no point in reading the study any further. We discussed in a previous lesson whether a sample of women in Chinatown would give an accurate measure of the average woman's shoe size in San Francisco. Good graphs are extremely powerful tools for displaying large quantities of data. They let the reader see at a glance what the trends are. Unfortunately, it is relatively easy to deceive or mislead the reader with graphs. Sometimes this is deliberate, sometimes it happens through poor choice in constructing the graph. The researcher can be so close to something that he thinks he is showing what he found, but the interpretation by new eyes is very different. The same thing can happen when teachers construct test questions or when you edit your own work. You tend to see what you want to be there instead of what may actually be. So let's look at some graph characteristics. The graph should have a title so you know what data you're looking at. Everything should be labeled. All the axes, or if it's a pie chart, all the sections of the pie chart should be clearly labeled. The source of the data should be given so you know where the data came from. If it's a pictograph, there should be a key telling you what the pictures stand for. Also, if it's a pictograph, the pictures should be of uniform size. The scale, does it start with 0, and if not, is a break clearly indicated? Are the tick marks evenly spaced? Here's an example of scaling and axis manipulation. A graph can be altered by changing the scale of the graph. The two graphs below represent the same data, but scaling of the vertical axis changes the impression of the magnitude of the differences. If you look at the graph on the right, you think the differences between whatever's being represented here are pretty significant. But if you look at the graph on the left, they're much less so. Take a look at this graph and see if you see anything that might be misleading. First of all, look at the title. This title tells the reader what to think, that there are huge increases in price. The scale moves from 0 to 80,000 in the same amount of space as 80,000 to 81,000. The actual increase in price is 2,000 pounds, which is less than a 3% increase. The graph shows the second bar as being 3 times the size of the first bar, which makes your eye see a 300% increase. Here's a more accurate graph. An unbiased title has been provided, which just simply says the average house price in pounds. And a scale with a regular interval is provided. This shows a more accurate picture of the increase. Take a minute to look at this graph and see why you think it might be misleading. Did you notice that the scale does not have a regular interval? This distorts the graph and makes it look like the biggest increase is between 1 and 2 when it actually is between 3 and 4. Between 1 and 2, the quantity increases from 0 to 8. Between 3 and 4, it increases from 4 to 16 for a net increase of 12, but it's a much smaller line. Graphs can be misleading in the news. The margin of error is the amount, usually in percentage points, that the results can be off by. Be wary of data with large margins of error. A 2% margin of error would mean the true value for a reported value of 25% could be anywhere between 2% below that at 23% or 2% above the reported value, which in this case would be 27%. Margins of error of 1 or 2% are fairly common. This graph represents the 3D effect. What do you think is wrong with it? First of all, the vertical axis has no scale, and the perspective makes it appear that sales for 1995 were much greater than those for any other year when they were in fact equal. An improved graph is on the right. You can see that the sales in 1995 and the sales in 1997 were actually equal to each other. If you look at the graph at the top, it looks like 1995 was taller than all of the other years. Pictograms use pictures to show data. They are a catchy way to show data, but are not generally as accurate as other graphs. Notice in the example below there is no way to represent less than 5 apples. A whole apple represents 10 apples, and a half an apple represents 5 apples, and you can't represent any single apples less than 5. Here's another pictograph. What might be wrong with it? We have a scale. The dog represents 50 people, the cat represents 50 people, the horse represents 50 people, and the fish represent 50 people who had fish as pets. First of all, there's no category for those people who do not own a pet. Then we notice that the pictures are not the same size, giving the impression that the larger animal represents more when in fact they all represent 50. Does a glance at the graph leave you with the impression that the same number of people own horses and fish? See, there are 3 fish down there, and there are 3 horses, and each one stands for 50, so there are 150 people who have horses for pets and 150 who have fish for pets, but that's certainly not the impression you get when you look at that graph. Now let's look at pie charts. The following represents the results of a survey to determine what food to serve at a party. Do you notice any problems with it? The percents do not sum to 100. Is the math wrong, or is there a category missing? And we have no way of knowing that as the reader. The area of the slices also does not match the percent. A slice representing 10% of the data should occupy 10% of the pie. The 50% piece is perhaps easiest to visualize since half is easy for most of us to see, and clearly the chocolate fountain section is bigger than half of that pie. Here's an improved chart representing the same data. Software was used to get the geometry correct. Otherwise, you would have to get out a compass and protractor to draw your circle and measure the angles. Here are line graphs. The graphs below both represent the same data, the number of graduates at a community college for years 1999 through 2003. What are your comments on those two graphs? Clearly, the graphs give two different impressions. Graph A conveys the message that there has been a sharp decline in the number of graduates. Graph B makes the decline look less dire. No rules were broken. I left off the title and axis labels to save some space. But the graphs look different because the scales on the vertical axis are different. This is the author's choice, but illustrates that the reader needs to pay attention to the details. A college administrator is going to like the B graph better because it makes the decline enrollment seem smaller. Here's a graph from CNN.com. The question was, based on what you have learned or read about the case, do you agree with the court's decision to have the feeding tube removed? When we look at that graph, the difference in percentage points between Democrats and Republicans and between Democrats and Independents is 8%, 62 minus 54. Since the margin of error is 7%, it is likely that there is even less of a difference. So let's go back and look at that again. It looks like there's a wide difference between Democrats and Republicans. And you can see down here at the bottom where your margin of error is. The graph implies that Democrats were 8 times more likely to agree with the decision. In truth, they were only slightly more likely to agree with the decision. The graph does not accurately demonstrate that a majority of all groups interviewed actually did agree with that decision. They were all over 50%. Then CNN.com updated the graph to more accurately reflect the truth of the survey. When you look at this, you notice that there's not much difference between Democrats, Republicans, and Independents on this question. What does the top of this graph show? About 12 million people are downloading music legally, if you look at the top bar, and just over 9 million people are downloading music illegally. We notice on the bottom bar. The bottom of the graph is misleading. Why? And it's talking about the part where it says, but 1 billion iTunes songs don't account for what's filling our iPods. The graph implies that 1% of the iPods are filled with legally downloaded music. It implies that the other 99% are filled with illegally downloaded music. Why is that wrong? What could be in those iPods besides legally downloaded music, filling that other 99%? Could just be empty space. Most people don't have iPods that are filled to capacity. Songs that were added from legally purchased CDs could be in some of that space. Games, calendars, or other applications could also be occupying some of that space. Songs that were downloaded illegally might also be there, but probably not the whole other 99%. It is possible that the rest of the iPod contains some illegally downloaded music, but it is unlikely that 99% of a person's iPod is filled with illegal music. The iPod graphic appeared in Wired magazine. A quote from the article said, "What's filling all the excess capacity? Well, despite the efforts of the Recording Industry Association of America, nearly 1 billion songs are traded on P2P networks every month." This article was trying to imply that all of the excess space is filled with illegal downloads, which is likely untrue. The statistics for the article were provided by the music industry, so this represents how knowing where the data comes from may add some light to how you should interpret the information. Now take the misleading graphs assessment. The password is caution.